Greetings everyone, welcome back to General Chemistry. Today's topic is chemical thermodynamics. Let's just get straight to it. So the first thing we want to make sure we know about when studying thermodynamics is the notion of entropy. Entropy. What is it? Some people will tell you that entropy is a measure of the disorder of a system. Some people will tell you that entropy is a measure of the disorder of a system. They'll tell you that a room that's nice and clean and well organized has low entropy, while a room that is messy has very high entropy. But that's just not true. That's completely wrong. Entropy is not disorder. Disorder is what a lot of teachers will go to in order to explain entropy because they don't want to go into the math because maybe they know their students will tune out if you try to explain what entropy really is. But you know me, I always say chemists are not mathematicians and the math is important. I'm going to go into the math. Entropy is not disorder. It's associated with disorder, and we'll see why later. So what is entropy really about? In order to understand it, let's go ahead and put together the example of 4 particles on a grid. Let's say you've got a grid that has 4 spaces available. And in each of these spaces, one of 4 particles will randomly be assigned. So for now, let's say particle A is in space 1, particle B is in space 2, C is in space 3, and D is in space 4. Now, if I'm going to arrange these 4 particles randomly in these 4 spaces, how many ways are there to arrange these? I could have, here's another possible arrangement, I could have B here, and D here, and A here, and C here. So that's another possible arrangement. And it turns out that there's a total of 24 of these. If you remember basic probability and working with factorials and all that, then maybe you'll be able to see that pretty easily. But yeah, if you have 4 spaces, then for particle A, there's 4 different places where you could put it. Then after placing particle A, you have 3 possible places to place particle B. Then after placing particle B, there's 2 spaces left where you could place particle C, and then there's 1 space left for particle D. So that's 4 by 3 by 2 by 1. That's a total of 24 possible arrangements, 24 possible configurations or states. 24 configurations or states. Okay, what if I expanded the grid? What if I expanded the grid? Instead of making it a 2 by 2 grid, let's say that the same 4 particles now have more room to occupy. Now it's a 4 by 4 grid, and there's a total of 16 spaces to occupy now. Still 4 particles, but 16 spaces to occupy. Now, how many configurations are there? Well, there's 16 places to place particle A, and that leaves 15 possible spaces to place B, and 14 possible spaces to place C, and 13 possible spaces to place particle D. That's a total of how many configurations? Let's get out our calculator. So that's going to be 16 by 15 by 14 by 13 is 43,680. 43,680 possible configurations. or states. I'll just say states because it's a shorter word. Okay, so we went from 24 to 43,680 possible states. Now, what if I was only interested in the states where the four particles were clustered together like they were in the original 2x2 grid? What if I was only interested in states that looked like this, having your four particles in these four spaces clustered together, for example? Or maybe states that look like this. Any and all states in which the four particles are still clustered in the same 2x2 space within this 4x4 grid. How many of those kinds of states exist? Well, let's see. So there's, of course, for every 2x2, what's the word I'm looking for? For every one of these possible 2x2 arrangements within the 4x4 grid, there's going to be 24 configurations. So there's 24 ways for four particles to be in the top left corner of your 4x4 grid. There's 24 ways to have them in the top right corner over here. There's 24 ways to have them in the bottom left and 24 ways to have them in the bottom right. So that's 4 times 24 so far. There's 24 ways to have them in a state like this. There's 24 ways to have them over here, mid-left. There's 24 ways to have them in the middle of the top. And there's 24 ways to have them mid-right. So that's 8 times 24 is, let's see, 8 times 24, 192. So there's 192, I guess you can call them ordered states. In which the four particles are clustered close together like they were in this original 2x2 grid. And all other states, the particles are going to be pretty much spread out and scattered and not so orderly. So the reason why this 4x4 grid has a higher entropy isn't because it's more disorderly, it's because it makes disorder more probable. It's because it makes disorder more probable. To keep a quote-unquote orderly arrangement, the probability of that happening is 192 out of 43,680. That's, let's calculate it. 192 over 43,680. That's less than 0.5%. The chances of that happening, the chances of the particles just randomly landing in four spaces right by each other is 0.44% almost. There's only a 0.44% chance of reaching one of these quote-unquote ordered states. So more than 99% of the time, you're going to be in a quote-unquote disordered state just because of the larger space. So the entropy isn't really a property of the particular arrangement, it's a property of the space and how many arrangements it allows for your particles. Entropy is not disorder. It's just that high entropy usually leads to a state that's more disorderly, because usually when we think of things as being disorderly, we think of the particles being scattered about in random corners of the space. And in big spaces, the probability of that is just so much higher. There's more configurations where that is the case than configurations where that is not the case. So a small, messy room still has lower entropy than a big, tidy room. It's all about the size of the system. Well, that's one part of it. The size of the system is part of it. But another part of it is the energy of the system. So if I had 8 units of energy, if I had 8 total units of energy in this system, 8 indivisible units, so you can't split any of these units in half or anything like that. It's all or nothing. Either you have the unit or you don't. It's the whole unit or no units at all. If you have 8 units of energy, then what you're most likely to see is each particle ending up with 2 out of 8 units. There's 4 particles. Getting 2 units each is the most probable outcome. But of course, there's a bunch of different ways that these 8 units of energy could be spread across the 4 particles. You could have all 8 units of energy concentrated in just one particle and no energy in the other 3. There's 4 of those configurations. One is when you have all 8 units on A and none on B, C, or D. Another is if you have them all on B. Another is if you have them all on C. Another is if you have them all on D. Then there's a bunch of configurations where one particle has 7 units of energy and one particle has 1 unit of energy. So, for example, you could have 7 on A and 1 on B, 7 on A and 1 on C, 7 on A and 1 on D, and then repeat that again with the 7 being on B, C, or D. And you could keep going down this list and count how many possible arrangements there are for the different distributions of energy. You could do 6-2 next. You could do 6-1-1 next. Whoops, I forgot my colon there. You can do 5-3, 5-2-1, 5-1-1-1, and just count all of the different ways in which the energy could be distributed across those particles. The more units of energy there are, and the more particles there are, the more ways there are to distribute the energies among those particles. So more energy also leads to more entropy. The more energy there is in a system and the more particles there are for that energy to be distributed across, the more possible configurations. On top of all the possible positions that the particles can be in. So take these 43,680 states and multiply them by however many energy combinations you can have for the particles in those states, and now you've got a ridiculously large number of states. So yeah, entropy is not disorder. If anything, entropy, I guess, measures... Well, I wouldn't even say it measures the spread of the particles in energy, because that's not true either. It measures the likelihood of the particles and energies being more spread out. Let's put it that way. Okay, so some other illustrations. I guess we can say that entropy explains the concept of diffusion, or the process of diffusion for gases and liquids. So here's a classic example that you see in most chemistry textbooks to help explain the concept of entropy. So on the left, you've got gas particles trapped inside of a chamber on the left-hand side of, I don't even know what they call this thing. What is it? It's like 2 flasks connected by a valve. So you've got gases on the in the left flask for the image on the left. When you go to the image on the right, the valve is opened, which allows for the possibility of the gas particles occupying the flask on the right. And even though it's technically possible by random chance for all the gas particles to end up exclusively on the right-hand side of this device, or for them to all end up exclusively on the left-hand side, even though that's technically possible, it's very, very highly improbable, so we never see it, and we never expect to see it in real life. The most probable arrangement is the one in which it's 50-50 or nearly 50-50. There's just way more of those 50-50 type configurations than there are of those 100-0 configurations. So that's for particles. For energy, well, I guess you could say that the higher probability of energy being more distributed helps explain why heat transfers from a hotter object to a colder object. So in this next diagram, they show you two systems, X and Y. X is at a higher temperature than Y, and the heat flows from X to Y. It is technically possible for heat to flow from Y to X. It is possible for heat to go from the colder object to the warmer object, but it's statistically unlikely to happen. So maybe we should talk about this a little bit more. If you've got two systems, one at a high temperature and one at a low temperature, and you have them in contact with each other in such a way that they are allowed to exchange energy with each other. What's more likely? If you've got energy that just kind of moves about randomly whenever it's free to move from particle to particle. If I have a bunch of particles in each system that can be carriers of energy, then what's more likely to happen? An energy transfer from a particle in here to a particle in here, or the reverse? Well, it's more likely for energy to jump from this side to this side. There's more energy here, and because there are more energy units, there's just more chances of outward transfers from this box as when compared to this box. Even if energy is being transferred from the box on the right to the box on the left, because it's less likely, overall, the amount of energy coming from the left to the right will outweigh any energy that's coming from the right to the left. So heat will just flow from high temperature to low temperature. Let me see. So I guess now is the time to develop the notion of microstates versus macrostates. So earlier I called these configurations or states, combinations of positions of particles and distributions of energies amongst those particles. That's what we would, any individual state is what we would call a microstate. So a microstate is a particular A microstate is a particular arrangement of particles and their energies. Any particular arrangement of particles and their energies. Within a system. So, all four particles being in the top left corner of this 4x4 grid would be considered a microstate. Actually, to be more specific, if I had A in here and B in here and C in here and D in here, that's a microstate. If I swap any two of these particles' positions, that's another microstate. So overall, 43,680 possible microstates. A macrostate, on the other hand, is basically a set of microstates that have something in common. A macrostate is a set of microstates. So, for example, whether you're in a 2x2 grid or whether you're in a 4x4 grid, those are two different macrostates. Being in a 2x2 grid is one macrostate, being in a 4x4 grid is a different macrostate. They actually have a pretty nice visual here for microstates. Well, two of them actually. One for positions of particles, and then another one for distributions of energies. So, yeah, if you have four particles and two boxes, and each box can contain a maximum of four particles, then you have a total of, let's see, how many microstates is that? So we've got 1 plus 4 is 5, and then another 5 there is 10, and 6. You've got 16. Oh, it's written down in the caption. Yeah, so you've got 16 possible microstates, all associated with a single macrostate, the state of having four particles and two boxes to distribute them into. Similarly, we've got, if you want to look at how energies are distributed without moving the particles, here the stars represent units of energy, so you've got a system where you've got two particles in box 1 and two particles in box 2, indicated by red and blue, and you've got two units of energy, two stars that can be arranged in different ways. So in set A, you've got all of the energy lies in the left-hand box of each configuration. So you've got both units of energy on A, both units of energy distributed between A and B, and then both on B. Then for set B, you've got one unit in each box, one in the red box and one in the blue box. And there's four possibilities for that. And then part C is set C is basically the reverse of set A, where both energy units are confined to the blue box, or the box on the right, for each microstate. So yeah, those are just more examples to help you kind of think through the idea. But that's the basics of entropy. It's really about probability and statistics in the end. Okay, so that's microstates versus macrostates. Where do we want to go next? So I guess now we can start talking about actual chemical systems. We can now start talking about actual chemical systems. Let me see. So basically, I want to qualitatively am I spelling that right? Qualitatively estimating the entropy of a system. Okay. Which system has more entropy to it? A glass of water, or a glass full of crushed ice. So here's a bunch of ice chunks, or my best attempt at drawing ice chunks anyway. Which of those two is likely to have a higher amount of entropy? If you think of entropy as disorder, then you will probably make the mistaken assumption that the crushed ice has the higher entropy because it's, well, more disorderly. I mean, you've got crushed pieces of ice that are jagged and random shaped versus the water that's so smooth and calm, and you would think based on that inferior definition of entropy that the crushed ice has the higher entropy, but that's not actually true. The truth is that the water has the higher entropy. Why? Think about how many different ways the particles can be arranged. Let's forget about the energies for a minute. Just think about the number of ways in which the particles' positions can be rearranged. Well, the crushed ice is in the solid state, and particles in the solid state don't have a lot of freedom of movement. They kind of just vibrate in place. They can move, but not by a whole lot. They just kind of shake. Whereas in the liquid phase, the particles can move around, and a particle that used to be near the surface of the glass can migrate all the way to the bottom, and a particle that was all the way at the bottom can migrate to anywhere else within the glass. Well, up to the surface of the water at least. So yeah, there's freedom of movement. There's more available options for each individual particle when you're in the liquid phase. So generally speaking, the more, well, I shouldn't say the more, but generally speaking, liquids tend to have higher entropies than solids, and gases tend to have higher entropies than liquids. Gases have even more freedom of movement because they're not even confined to a specific volume. Liquids have a definite volume, gases don't. Gases can change their volume, so they have lots of possible arrangements because they just have lots of possible system sizes. Remember, increasing the size of a system can dramatically increase the number of available microstates. So yeah, this is all summarized in the following little visual. I mean, there's nothing in there that I haven't explained already, but in case you need to see it in more detail, in case my drawings are too horrible to interpret, there you go. Solids have the lowest entropies in general, then liquids have higher entropies, and then gases have way more entropy. So if I were asking for the change in entropy which is a greater change in entropy, going from solid to liquid or going from liquid to gas? Going from solid to liquid increases the entropy by a great deal. Going from liquid to gas increases the entropy way, way more. The liquid to gas entropy change is way bigger than the solid to liquid entropy change. Keep that in mind for later. Now, entropy has a little bit of a title to it in the realm of physics. Physicists sometimes like to call entropy the arrow of time. Physicists like to call entropy the arrow of time. If it weren't for entropy, we wouldn't know that time is going forward. Basically, the idea behind this is that as time progresses, as time moves forward, the total entropy within the universe has to increase. And that's the second law of thermodynamics, by the way. We covered the first law in video number 6. First law said that the total energy in the universe is conserved. The second law of thermodynamics, second law, not second law. Second law of thermodynamics says that over time, and I see this marker is fading. Let me switch to another one. Well, this new one is also kind of pink. Second law of thermodynamics says that the entropy of the universe will always increase for any spontaneous process. Will always increase for any spontaneous process. And for a non-spontaneous process to occur, you have to create an increase in entropy that at least compensates for the decrease in entropy that would result from that non-spontaneous process. We'll talk about what spontaneous means in a bit. The entropy of the universe will always increase for any spontaneous process. Well, I guess I can define spontaneous now. So a process is spontaneous if it happens of its own accord. A process is spontaneous if it happens of its own accord. That is, it happens on its own. You don't need to put any energy into making it happen. So, for example, if it's cold outside and I leave out a cup of water and I come back an hour later, it will have frozen into a block of ice. That just happens spontaneously. I don't do any sort of external work to make it happen. That's just what naturally happens to water at cold temperatures. On the other hand, if I bring that block of ice back inside where it's warm, then it would spontaneously melt, because that's just what ice does when it gets warm. I don't need to force the ice to melt by, I don't know, running electricity through it or something. It'll just happen on its own. It'll happen spontaneously. So there's a mathematical version of the second law of thermodynamics which says delta S universe, delta S of the universe, is always going to be greater than or equal to 0. Well, greater than 0 for spontaneous processes, equal to 0 for what's called a reversible process. We won't talk about what reversible processes are because that's more of a physics thing. So I guess for chemistry purposes, delta S universe is greater than 0. And delta S universe, by the way, equals delta S of your system plus delta S of your surroundings. What on earth is delta S? Well, that's the symbol for the change in entropy. That's the symbol for the change in entropy. So S is the symbol that we use for entropy, and delta S is the change in entropy of a system. So yeah, once you've defined your system, the rest of the universe is the surroundings. If the entropy of your system decreases, then the entropy of the surroundings must increase by at least as much in order for the second law of thermodynamics to hold. Now, there is one case in which a delta S universe doesn't have to be greater than 0, and that is for any process that occurs at a temperature of 0 kelvins. That's the third law of thermodynamics. That's the third law of thermodynamics. So, third law of thermodynamics says that the entropy of a system, at absolute 0, a system at 0 kelvins, is 0. The entropy of a system at 0 kelvins is 0. And maybe I should strike through that so that people don't confuse it for an O. And maybe I should write out the word Kelvin. At 0 kelvins is 0. So there you go. You've learned all the laws of thermodynamics. Well, not quite. There is also something called the 0th law of thermodynamics, which defines temperature. I feel like I may have mentioned it in video number 6, but I don't remember. But this is just kind of FYI stuff at this point. 0th law of thermodynamics says that if two systems are in thermal equilibrium with a third system, then they are in thermal equilibrium with each other. Then they are in thermal equilibrium with each other. What on earth does that mean? I'll explain. Then they are in thermal equilibrium with each other. So, earlier we were talking about heat flow and how heat flows from high temperature to low temperature, and how some heat could actually flow from the low temperature system to the high temperature system, but because more heat goes from high to low, overall the heat flows from the high temperature object to the low temperature object. So This should kind of sound familiar in the context of the past 3 videos when you've got things going both ways, but maybe the forward process occurs faster than the reverse process until eventually they reach a point where both processes in both directions are happening in equal amounts and at equal rates. Yeah, it's equilibrium. That's what thermal equilibrium is. So instead of reactants and products converting into each other at equal rates, in the case of dynamic equilibrium or chemical equilibrium, thermal equilibrium is about heat going forward and backward at equal rates. So when two things are in thermal equilibrium with each other, that means that they're at the same temperature. That's just another way of saying they're at the same temperature. So if two systems are in thermal equilibrium with a third system, if I've got system A and I make it touch system C, and I don't notice any heat transfer, at least no overall heat transfer, and I then take system B and put it in contact with system C, and no heat transfer happens, then even without putting systems A and B together, even without making systems A and B touch each other, because they both are in thermal equilibrium with C, I know they're in thermal equilibrium with each other. So essentially, system C is a thermometer. If I stick a thermometer in A and it gives me a reading, and I stick a thermometer in B and it gives me the same reading, then I know, without putting A and B together, I know that even if you were to put them together, no heat would flow between them. At least no overall heat. Again, it's an equilibrium thing. There is actually heat flowing, but it's equal amounts in both directions at the same time, so it's effectively like there's no heat being transferred. So yeah, that's the 0th law of thermodynamics, and if you're wondering why they started counting at 0, well, they didn't intend to do that. The first law of thermodynamics was simply discovered first, but the 0th law of thermodynamics logically should come before the first. You need some notion of temperature before you can talk about conservation of energy. And that's why the 0th law is the 0th law, to emphasize that it logically should come before the first, even though the first law of thermodynamics was discovered before the 0th law. And if you're wondering about the specific order in which all 4 laws of thermodynamics were discovered, you're going to have to ask a historian, because I don't know. Maybe I'll Google it and post it in a pinned comment or something, but don't count on it. Let's see. So we got a little sidetracked with the laws of thermodynamics there. So the second law of thermodynamics is the one that you want to focus on for the remainder of this chapter. The entropy of the universe will always increase for any spontaneous process. The natural thing for systems to do is for the particles within them to spread throughout the available space, and for the energy to spread among the available particles. That's the natural thing that happens over time. And that's why eventually the universe will die because of heat death. The energy will just get spread out more and more and more throughout the universe until there's just not enough energy concentrated in the right spaces for you to achieve anything, really. And then there are different theories as to what happens, but I think the most popular one, and probably the most accepted one, is that it'll be a reversal of the Big Bang. But now we're getting too physicsy. before we do some problems, I need to talk about the notion of standard conditions. So when we do thermodynamics, we're going to talk about standard conditions a lot. In thermochemistry, we define standard conditions as being a pressure of 1 atmosphere and a temperature of 25 degrees Celsius. For gas laws, we defined standard temperature to be 0 degrees Celsius, 273 kelvins, and the standard pressure was still 1 atmosphere. In thermodynamics, standard conditions means two things. Standard conditions in thermodynamics means two different things. If you're dealing with aqueous substances, then standard concentration is 1 molar. And if you're dealing with gases, then partial pressures, standard partial pressures are 1 atmosphere. And there is no standard temperature. There is no standard temperature. Oh, there's another thing I forgot to mention. Well, two things actually, now that I think about it. There are two other things I forgot to mention. Change in entropy. So, change in entropy can work in a manner very similar to change in enthalpy. Delta S is very similar to delta H in that delta H can be calculated by taking the heat of the products minus the heat of the reactants. Delta S can be computed in a similar way. It's the entropy of the system in its final state minus the entropy of the system in its initial state. And if your system is, well, a reaction, then it's the entropy of the products minus the entropy of the reactants. However, there is one other way to calculate change in entropy, and that's for when temperatures don't change. For a constant temperature process or isothermal process, you can calculate delta S as the change in heat of the system divided by the absolute temperature. And through this definition, you can see that the units for entropy are going to be joules per Kelvin. At least those are the standard units. Joules per Kelvin. All right. I think that's everything. No, there's one more thing. Unlike enthalpy, where you just have to pick something and set it to 0, entropy is actually well defined. Remember, entropy is based on the number of microstates, the number of configurations there are for a system. So there is an absolute entropy that you can calculate. And I guess this actually ties into the third law of thermodynamics. There is actually a formula. It's Boltzmann's equation. It's the Boltzmann equation. My oh my, have we heard a lot about Boltzmann. I think it was a double N. The Boltzmann equation. We've brought up the Boltzmann distribution however many times, and now another contribution from Boltzmann. The Boltzmann equation defines entropy as little k times the natural log of W. K is Boltzmann's constant. K is the Boltzmann constant, which is equal to 1. Let's see if I'm remembering this right. 1.38 times 10 to the negative 23rd, I think. It's the ideal gas constant divided by Avogadro's number, if I recall correctly. 8.314 joules per mole Kelvin divided by 6.022 times 10 to the 23rd. Yeah, 1.38 times 10 to the negative 23. That's joules per Kelvin. And then the natural log of W. W is the total number of microstates. Total number of available microstates within a system. Total number of microstates. Oh my goodness, it looks like all my markers are fading tonight. That's okay. I think I have like 2 or 3 new sets of markers that have yet to be opened. I'm guessing one of them will be opened tonight. So, of course, you're not gonna be asked to calculate the total number of microstates because, you know, it's hard. It's real hard. I mean, I imagine that just this calculation alone was hard enough for some people to follow along with. They're not going to make you do that. Maybe in a physics class, maybe, but in chemistry, definitely not. So really you just kind of need to know about this. One thing though, this ties into the third law of thermodynamics. The entropy of a system at 0 kelvins is 0. Why? Because at 0 kelvins, there's literally no energy, so a system of particles at 0 kelvins cannot move. They cannot change their positions, and there's no energy that moves between particles either, so there is no change in configurations. There is no change in microstates. There's only one microstate available. You're frozen and locked into one single microstate that can never change until, of course, you raise the temperature. So if there's only one microstate, what's the natural log of 1? It's 0. So K times 0 gives you an entropy of 0. So the only time entropy is 0 is at 0 kelvins, and for every other system, it's going to be some positive number. Well, is it? Well, yeah, because W can't be a fraction, and oh, actually, it could be negative for 2, but not for 3, because it's log base E. Okay, so I guess there's just one specific case where entropy could be negative. Entropy change can be negative, but absolute entropy for the most part will always be a positive number, unless you happen to discover that one system in the universe that may or may not exist that only has 2 available microstates. Good luck with that. Okay, let's look at some problems. Let's have a look at some problems. Okay, number 1, what is a spontaneous reaction? We've already defined spontaneity. A spontaneous process is one that occurs without the need for any outside work. Even if a process is endothermic, it doesn't necessarily mean that it's non-spontaneous. The melting of ice is endothermic, yet it happens spontaneously at warm temperatures. You're not actively heating the ice cube or trying to direct energy towards it deliberately. It just happens to gather energy from the surroundings on its own, and the process occurs without your interference. So that's spontaneous versus non-spontaneous. What about number 3? Indicate whether the following processes are spontaneous or non-spontaneous. Technically, you can't base it off of entropy alone, but I'm guessing for now they just want you to go with entropy. Liquid water freezing at a temperature below its freezing point. We already did that example. That's spontaneous. Liquid water freezing at a temperature above its freezing point. To make water freeze at room temperature, yeah, you're going to need to put in some work to make that happen. Pressurize it or do whatever it is you have to do to make liquid water freeze. And no, putting it in the freezer doesn't count. You have to keep its temperature at whatever that warm temperature is while making it freeze. The combustion of gasoline would be spontaneous. Once you have it ignited, of course, it'll just continue on its own. But yeah, the combustion of gasoline, I would say, is spontaneous. A ball thrown into the air, I would say that's non-spontaneous. The natural thing for balls to do is to fall down, not rise up in the air. So you had to put in work to make the ball go up. Part E, a raindrop falling to the ground, that's spontaneous. It's just gravity at work. Part F, iron rusting in a moist atmosphere, that would be spontaneous. If you leave iron out in a moist atmosphere, it will just rust on its own without any interference. Okay, 4, helium-filled balloon spontaneously deflates overnight as helium atoms diffuse through the wall of the balloon. Describe the redistribution of matter and or energy that accompanies this process. Yeah, I'm not entirely sure what they want, but we already talked about diffusion. If more space is available for the particles to occupy, then just based on probability alone, if the particles are moving randomly, or, well, it's not random, it's just that the motion of gas particles is so unpredictable that it might as well be random. But yeah, if they're moving about randomly, then there's just more chances to occupy the wider space than there is to stay confined to the volume of the balloon. And that's why diffusion happens. The scattered distribution outside the balloon is just more likely than having the helium particles stay in the balloon. Number 5. Is that anything new? Many plastic materials are organic polymers that contain carbon and hydrogen. The oxidation of these plastics in air to form carbon dioxide and water is a spontaneous process. However, plastic materials tend to persist in the environment. Explain. Just because the process is spontaneous doesn't mean it happens quickly and in an instant. It takes time. That's the problem with plastics. It's not that they don't decompose, it's that they take forever to decompose. That's for the environmentally conscious people out there. Okay. Next set, we've got in figure 16.8, all possible distributions in microstates are shown for 4 different particles shared between 2 boxes. Determine the entropy change if the particles are initially evenly distributed between the 2 boxes, but upon redistribution all end up in box B. Okay, let's see. So if I go back to that figure, let's see. They said, determine the entropy change if the particles are initially evenly distributed between the 2 boxes. So that's like state C. Okay, so I guess they're counting the whole set C as a single macrostate. And then set B is another macrostate. So you're changing from 6 configurations to 4 configurations. You can just use the Boltzmann equation for this. Yeah, there's 6 configurations in set C and 4 configurations in set B. So let me switch back to the document camera actually. So yeah, delta S is S final minus S initial equals K natural log of, what was it again? 4 states and, yeah, 4 states versus 6. So the final state is 4 states minus K times natural log. The initial set had 6 microstates. K times natural log of 4 minus K times natural log of 6. If you factor out the K, that's K natural log of 4 minus natural log of 6, which is the same as natural log of 4 over 6 if you take advantage of the logarithm properties. And yeah, from there I'm guessing delta S is going to be a negative number because you went from 6 configurations to 4. That's a reduction in entropy. So 1.38 times 10 to the negative 23 times ln of 4 over 6 is negative 5.60 equals negative 5.60 times 10 to the negative 23 joules per Kelvin. Oh. Let me hold that down. There we go. That's better. My inner neat freak. There we go. No, that doesn't look right either. I don't have OCD, I swear. Okay, moving on. Number 7, is it going to be the same as number 6? Determine the entropy change for the system when it's converted from distribution B to distribution D. There's going to be no entropy change in that case because it's the same number of microstates. Distribution B and distribution D are both going to have 4 microstates in each set, so no change in entropy there. Number 8, how does the process described in the previous item relate to the system shown in 16.4? Do I actually have that figure? Where's 16.4? Oh, I do have it. It's this figure right here, but how does the process described in the previous item relate to the system shown in figure 16.4? I mean, you're increasing the amount of available space for the particles to move around in. There is an increase in entropy, so I would relate problem 8 to problem 6. I would relate problem 8 to problem 6, but not to problem 7. I'm not really sure where they're going with this. Anyway, moving on. Number 9, consider a system similar to one in figure 16.8, except that it contains 6 particles instead of 4. What is the probability of having all the particles in only one of the 2 boxes in the case? Compare this with the similar probability for the system of 4 particles that we have derived to be equal to 1/8. What does this comparison tell us about even larger systems? Let's see. Well, the probability, if we're just assigning the particles randomly to one box or the other, then there's a 1 in 2 chance for the first particle to be in the left box and a 1 in 2 chance for the second, times a 1 in 2 chance for the third and the fourth and the fifth and the sixth. So it's 1/2 raised to the 6th power. You probably don't need to know this for your chemistry class, but if you know your math and you know your probability, then this shouldn't be much of a challenge to you. Yeah, the probability is 1/2 times a half times a half 6 times. It's 1/2 to the 6th, which is, I believe, 1 in 64. Is that right? Yeah, 1 in 64. Okay, so what else were they saying? What is the probability of having all the particles in only one box? 1 out of 64. Compare this with the similar probability for the system of 4 particles that we have derived to be equal to 1 out of 8. What does this comparison tell us about even larger systems? Wait, it's not 1 out of 8 for 4 particles. Why is it 1 out of 8? It should be 1 out of 16. Oh, okay. I know why. I know why it's 1 out of 8. Because I forgot. So it's a 1 out of 64 chance for all 6 particles to be in the left box, plus a 1 out of 64 chance for them all to be in the right box, which means it's a total of 2 out of 64. It's a 2 out of 64 chance to be all in one box or all in the other. Okay. And that's how they got 1 out of 8 instead of 1 out of 16. Okay. So back to what it was saying. What does this comparison tell us about even larger systems? The bigger the systems, the bigger the sets of possible microstates. And yeah, the more entropy you can have. I'm not really sure what else they want you to do here. I mean, it really is that easy. This chapter isn't particularly hard in terms of what you need to be able to do. It's just, it can be a challenge in terms of wrapping your head around these new concepts. Number 10, consider the system shown in figure 16.9. I'm guessing that was the one with the energies. Yes, it was. Yeah, they're talking about this. Anyway, what do they want? What is the change in entropy for the process where the energy is initially associated only with particle A, but in the final state the energy is distributed between 2 different particles? Okay, so you would have to count, let's see, there's only one state in which both units of energy are in particle A, and then distributed across 2 particles, there's how many of those? There's A and B, there's A and C, there's A and D, there's B and C, there's B and D, there's C and D. So how many are those? That's 1, 2, 3, 4, 5, 6. So there's 6 configurations where that happens. basically do the same thing that we did for problem number 6, I believe. Yeah, S final minus S initial using the Boltzmann equation, which, again, you're probably not going to have to use in your chemistry class anyway. Number 11, I'm guessing, is more of the same, so we'll skip. 12, arrange the following sets of systems in order of increasing entropy. Assume 1 mole of each substance and the same temperature for each member of a set. Oh, I forgot to mention, now that they bring up assume 1 mole. So if you increase the number of particles, that also increases the number of possible configurations. So if I go back to my this grid thing, so expanding the grid increases the number of possible states. Increasing the number of particles also increases the possible number of states. What if I had 2 more particles, E and F? What if I had 2 more particles, E and F? Well, now it's 16 places for particle A times 15 possible places for particle B times 14 for particle C times 13 for D times 12 for E and times 11 for F. So that increases the number of possible microstates by a factor of 12 times 11 is 132. And I know that because I'm a nerd. So yeah, increasing the number of particles can also increase the entropy. But usually the effect of expanding the space is more significant. Anyway, assuming that the number of particles is the same, what do we have? We've got hydrogen gas, perbromic acid gas, and hydrobromic acid gas. Arrange in order of increasing entropy. So what is the difference between those three? They're all 1 mole of gas, and they're all in the gas... they're all 1 mole, and they're all in the gas phase. So what is the difference between them that could create differences in their entropies? Well, hydrogen gas is going to be the smallest in terms of particle size. So if they occupy the same volume, then there's more places for the hydrogen particles to occupy. They can fit themselves into those nooks and crannies that the other 2 gases can't. Hydrobromic acid is bigger, but not as big as perbromic acid. So yeah, I would just guess based on individual particle size. The biggest particles have the least number of arrangements available to them. If you have the same size space, bigger particles have less options in terms of ways they can fill that space. So I would say hydrogen gas has the highest entropy, then HBr, then HBrO4. Part B, water, liquid, solid, gas state. You already know how to do that. I'm not going to answer it for you. Part C, helium, chlorine, and phosphorus, all in the gas phase. Pretty similar to A. Base it on size. Okay, next up, we've got at room temperature, the entropy of the halogens increases from I2 to Br2 to Cl2. Explain. Size. Cl2 is the smallest, so given the same volume, there's just more possible configurations, more spaces that those smaller particles can occupy. 14, consider two processes, sublimation of solid iodine and melting of solid iodine. Note the latter process can occur at the same temperature but somewhat higher pressure. Okay, is delta S positive or negative in these processes? Positive. The entropy final is greater than the entropy initial. Gases and liquids both have more entropy than solids in general. In which of the processes will the magnitude of the entropy change be greater? From solid to gas is a much bigger entropy change than from solid to liquid. I can't talk today. 15, indicate which substance in the given pairs has the higher entropy value. Explain your choices. We've got C2H5OH or C3H7OH. For this you would need to know a bit of organic chemistry, but it's C3H7OH because it's got more... the molecule itself has more possible arrangements. The molecule itself has more possible arrangements. So I guess I can pull out my modeling kit and show you how that works. So here's C2H4. So you've got a carbon here and a carbon here, and then C2H4? No, C2H6. My bad. So you've got a carbon here and 3 hydrogens, and a carbon here and 3 hydrogens. Okay, and they have a couple of different configurations because, they're free to rotate around the single bond. So there's a couple of different redistributions, but overall it's kind of a small difference. Now, what happens if I attach another carbon along with its accompanying hydrogens over here? Okay, well, now there's more freedom of movement. There's more arrangements possible, not only from the rotation of individual carbons around bonds around the ends and the rotations of the attached hydrogens, but also just the rearrangement of the whole entire shape of the molecule. If we make the molecule bigger and bigger and bigger, then the number of ways in which it can contort itself gives you way more options. I can't fit that whole thing on the screen, can I? Yeah, it doesn't look like you can see it all at the same time. But if I were to just twist this and rotate it around a bit, you can probably see all the different ways in which this thing can rearrange itself. So yeah, more carbons attached to a chain for an organic molecule, the more possible configurations it can be in just within the molecule itself, let alone all the possible spaces within the volume that the molecule can occupy. Just rearrangements of the molecule itself adds more possible configurations, more possible microstates. Okay, so for A, I would choose C3H7OH, propanol. Part B, we've got a liquid versus a gas. The gas is going to have substantially more entropy. And then part C, 2 moles of monatomic hydrogen versus 1 mole of monatomic hydrogen. More particles, more entropy. So it's the 2 moles. 16, predict the sign of the entropy change for the following processes. An ice cube is warmed to near its melting point. So the entropy change would be positive. If you add heat, if you warm it up, then you're adding energy, and with more energy, there's more possible configurations of those energies. There's more possible ways for those energies to be distributed across the particles. Part B, exhaled breath forms fog on a cold morning. I would say that's a decrease in entropy because you're taking water vapor and it's condensing to liquid water. And then snow melting, that's from solid to liquid, so that's an increase in entropy. All right, what else do we have here? Predict the sign of the entropy change for the following processes. Give a reason for your prediction. From free-floating ions to solid lead to sulfide. That's a decrease in entropy because you're going from aqueous to solid. Aqueous is pretty much the same as liquid as far as entropy is concerned. So yeah, aqueous substances and liquids have pretty much the same entropy, relatively speaking, and gases have more entropy than liquids, and aqueous substances and liquids and aqueous substances have more entropy than solids. Part B, you've got a solid and a gas turning into just a solid. Well, if you're losing gas, that's a significant decrease in entropy. So for B, delta S is going to be negative. For C, it looks like you're going from, let's see, you've got liquid and gas on the left and gas on the right. And there's more gas on the right than there is gas on the left. So yeah, between 26 moles of gas on the right and 19 moles of gas on the left, if there's more moles of gas on the right, then that's an increase in entropy. At least that's the prediction. Problem 18, write the balanced chemical equation for the combustion of methane to give carbon dioxide and water. Explain why it is difficult to predict whether delta S is positive or negative for this chemical reaction. Let's see. Combustion of methane. So it would be CH4 plus O2 giving CO2 and H2O. And both of those are in the gas phase, so it's not liquid water. Oh, I see, because everything is a gas, so you'd have to go on the basis of the number of moles, but what is the number of moles? Let's balance this. So 1 carbon, 4 hydrogen, multiply that by 2, so now you've got 4 hydrogens, and then that's 2 times 1 is 2 oxygens plus 2 there, that's 4. Ah, now I see. The total moles of gas on the left is 1 plus 2 is 3, and the total moles of gas on the right is also 3. So it's 3 moles of gas versus 3 moles of gas. It's hard to tell where the higher entropy lies. Okay, that wasn't too bad. Number 19, write the balanced chemical equation for the combustion of benzene to give carbon dioxide and water vapor. What do you expect delta S to be positive or negative in this process? We've seen how this works, so I'll leave that one to you. I think between part C of 17 and problem 18, you've seen everything you need to see in order to figure that out on your own. What else do I have? What's the difference between delta S and delta S standard for a chemical change? That degree symbol means standard, and we'll see that again later in this video. So the degree symbol just means that it's measured under standard conditions, a pressure of 1 atmosphere for gases or a concentration of 1 molar for aqueous substances. Calculate delta S standard for the following changes. So to do this, you're going to need to use data tables, but It's very, very similar to how you calculate delta H. So if I go to, let's see, if I go to this window, is it on? No, not yet. Okay, hold on. There we go. Hopefully you can see this scrolling by, but just look at a chart like this. So you've got your heat of formation, your free energy of formation, we'll talk about this later, and your entropy values. And yeah, you can just look them up and perform whatever calculations are needed. I guess I'll just scroll through these real quick so that you can go back to this moment of the video and look up any values you need. Or you're probably better off with just downloading this book, which you can do for free at OpenStax. It's not one of those pirated things, it's just a legit Creative Commons textbook. But yeah, you've seen this before in video number 6. I think it's actually the same appendix even. Yeah, it should be. How long do these go on? Okay, and that's the end of that. So I don't think I'm going to pull that up again for the rest of this video, but there you have it. So just like you did with delta H values back in video number 6, it's not too hard to calculate delta S values. One thing they didn't specify for that table that I just showed you, those values are calculated for a temperature of 25 degrees Celsius, I believe. And that's not going to matter for the delta H and delta S, but it is going to matter for the delta G, as we will explain later. Well, technically it should matter for the delta H, but we assume delta H doesn't change with temperature to make our calculations easier. So based on that assumption, it doesn't matter for delta H. So yeah, 21 you can do on your own. Review the calculating delta H reaction from video number 6 if you've forgotten how to do that. 22, determine the entropy change for the combustion of liquid ethanol. Same as 21, except you have to write the reaction and balance it first. 23, determine the entropy change for the combustion of propane. Same as 22. Okay, next set. Thermite reactions have been used for welding parts such as railway rails. In metal refining, one such thermite reaction is that one given there. Is the reaction spontaneous at room temperature under standard conditions? During the reaction, the surroundings absorb 851.8 kilojoules per mole of heat. I mean, predicting spontaneity is based on Gibbs free energy and not just entropy. So I'm not sure why they're asking this so early on in the problems, because we haven't covered Gibbs free energy yet. But what you would do is you would take the delta G values and take delta G of products minus delta G of reactants And if delta G is negative, it's spontaneous. If delta G is positive, it's non-spontaneous. We'll talk about delta G later, so don't worry if you are confused right now. 25, use the relevant S values, or S standard values, I should say, listed in the appendix to calculate delta S standard for the following changes. Okay, I'll do one of them. Let's do part A. So we've got nitrogen plus hydrogen. Oh, wait. Oh, yeah, that's fine. It's doable. I was worried there for a minute that it would be too easy. I forgot. So, S values for elements in their naturally occurring state is not necessarily 0. You might recall from video number 6 that we defined the heat of formation for an element in its naturally occurring state to be 0. We will also define the Gibbs free energy to be 0 for raw elements in their naturally occurring states, but the entropy is a whole nother story. Entropy is a whole nother story. Let me go ahead and look up the S values for nitrogen, hydrogen, and ammonia. Let's see, there's nitrogen is 191.6. I guess I'll switch to my camera so you can see what I'm doing. Nitrogen is 191.6 joules per Kelvin. Hydrogen and ammonia. Let's see, ammonia is 192.8 joules per Kelvin, and hydrogen, where is hydrogen? I wonder if it was under the oxygen list. No? I guess I'll have to scroll up for it. Okay, hydrogen gas, 130.7 joules per Kelvin. Okay. Now, in the balanced chemical equation, and I guess I'll do it down here, it was N2 plus 3H2 gives 2NH3. So it's going to be 2 times 192.8 minus 1 times 191.6 plus 3 times 130.7, close brackets. Don't forget to distribute that minus sign. Oh, and I forgot to close my parentheses there. So 191.6 plus 3 times 130.7 is 583.7, and then 2 times 192.8 is 385.6. So 385.6 minus 583.7 is negative 198.1. So I get a total of, and I'll write it in green, I get a total of delta S standard equals negative 198.1. Okay, I think it's time for a new sheet of paper. Let's see what we've got next. Part B you can do on your own. 26, from the following information, determine delta S for the following. Oh, okay, so in this case they don't want you to look it up from data tables. They want you to just apply Hess's law and rearrange those three equations. Okay, not too hard to do. So, third equation and second equation I need to flip in order to get the nitrogen and the oxygen monatomic gases onto the left-hand side. And then to get nitrogen monoxide on the right, I can just keep the first equation as is. Okay. So I need to flip two of them and keep the third. So we've got N2 plus O2 giving 2NO. I keep that as is, and that's 24.8 joules per Kelvin. Very small entropy change. Not a surprise when you consider it's 2 moles of gas converting to 2 moles of gas. So it's not going to be a big difference in entropy because you're not really changing the number of particles substantially, nor is there any significant phase change going on. So you shouldn't expect a significant change in entropy in one direction or the other. Okay, and then the other two reactions are flipped, so that's going to be 2 monatomic nitrogen forming diatomic nitrogen, and since I flipped it, I will take the negative of the delta S, so it's negative 115.0 joules per Kelvin for that second reaction. The third one is 117.0, but when you flip it, it becomes negative 117.0, and that's 2 oxygen forming diatomic oxygen gas. Okay, if I add these together, then the N2 cancels out, the O2 cancels out, and I'm left with 2N plus 2O. I guess I'll make it a curly O. Gives 2NO with an entropy change of 24.8 plus negative 115.0 plus negative 117.0 is delta S equals negative 207.2. But this isn't our desired equation. This is 2 times our desired equation. So divide everything by 2, and we get N plus O yields NO, has a delta S standard of, let's see, it would be negative 103.6. Negative 103.6 joules per Kelvin. So there you go. Nothing too different from what we did before with enthalpy. If you remember everything we did in video number 6, then this shouldn't be too hard for you. 27. By calculating delta S universe at each temperature, determine if the melting point of 1 mole of solid sodium chloride is spontaneous at 500 degrees Celsius and 700 degrees Celsius. So we've got 72.11 joules per mole Kelvin, 95.06 joules per mole Kelvin, and the heat of fusion is 27.95 kilojoules per mole. Okay, so I guess we can use that delta S formula for isothermal processes. So at 500 Celsius versus 700 Celsius, I'll just do one of them and you can do the other on your own. Let's do 500 Celsius. So 500 Celsius is the same as 773 kelvins. Okay, then they said S for solid sodium chloride is 72.11, and for liquid it's 95.06. So 95.06, so delta S from solid to liquid, it's 95.06 for the liquid minus 72.11 for the gas. Equals, what is that? 23.0, or no, that's not right. Let's just put it in the calculator and be safe. 22.95. 22.95 joules per mole Kelvin. Okay, then we've got, well, I can calculate delta S of the so that's delta S of the system. What about delta S of the surroundings? So delta S of the surroundings is going to be Q of the surroundings, the amount of heat absorbed or lost by the surroundings, over the temperature of 773. Now, the heat gained or lost by the surroundings equals the negative heat gained or lost by the system. That's according to the first law of thermodynamics. And negative Q system is just equal to negative delta H fusion. Is equal to negative delta H fusion. And I really should use the standard symbol here, but you know, it's not all that consequential. Okay, so delta S surroundings is going to be, let's see, heat of fusion is 27.95 kilojoules per mole. My delta S is in joules per mole Kelvin, so I'm going to need to convert that to joules. So that's 27.95 times 10 to the 3, or actually the negative of it because it's negative delta H fusion. Whoops. Let's see, is that right? Negative 27.95 times 10 to the 3 divided by a temperature of 773 is going to be negative 36.16 joules per mole Kelvin. And if you calculate the total delta S of the universe, delta S universe equals delta S system plus delta S surroundings, 22.95 plus negative 36.16. 22.95 plus negative 36.16, which overall is negative, which tells us, according to the second law of thermodynamics, that this is not a spontaneous process. If it were a spontaneous process, delta S universe would be positive, not negative. So there must be some external work being done. There must be some additional process being used that generates energy, a spontaneous process, and the delta S for that process must be big enough so that it generates a delta S that's positive enough to completely cancel out, if not overcome, the negative delta S universe that we have here. Because at the end of the day, the total entropy change of the universe must be a gain, must be an increase. Okay, so you can try it again for 700 degrees Celsius and see if that changes anything. I guess it would, because it would lower the value of delta S surroundings, maybe make it less negative to the point where its magnitude is less than 22.95. But yeah, that's how you would go about that one. Let's have a look at one more set before we talk about delta G. So 28 says use the standard entropy data in the appendix to determine the change in entropy for each of the following reactions. All the processes occur at the standard conditions and 25 degrees Celsius. Okay, so that's just using the data tables. You know how to do that. 29. I don't see how 29 is different from 28. Yeah, 29 is just asking you to do 28 again. That has to be some sort of oversight. Yeah, 28 says use the data to determine the entropy change, and 29 says use the data to determine the entropy change for those same problems. Okay, that's weird. But it is what it is. Okay, now let's talk about spontaneity a little bit more. So for a spontaneous process, delta S universe is greater than 0, is positive in other words. And delta S universe, of course, is equal to delta S system plus delta S surroundings. I'm going to write it as delta S surroundings plus delta S systems. Delta S surroundings plus delta S system. Is that what I said a few seconds ago, or did I say that wrong? Oh well, I'll figure it out when I'm reviewing the video later. Maybe I should have had some tea before I started recording. Where was I going? Right, so delta S for the surroundings, if we apply the same kind of thinking that we did with this last problem we did, then delta S of the surroundings is negative Q of the system over the absolute temperature. So we can say delta S universe equals negative Q system over T plus delta S of your system. Now, If your system is a chemical reaction occurring under constant pressure, then Q system is simply equal to the enthalpy. So we have delta S universe equals negative delta H of the reaction over T plus delta S of the reaction. If you multiply this whole equation across by negative T, then you get negative T delta S universe equals delta H of the reaction minus T delta S of the reaction. So for a spontaneous process, delta S universe is positive, which means negative T delta S universe is negative. Negative T delta S universe, we give this a special definition. This is what we call the Gibbs free energy. This is what we call the Gibbs free energy, so we relabel it delta G of the reaction is equal to delta H of reaction minus T delta S of reaction. So that's the Gibbs free energy. Gibbs free energy, or just free energy if you prefer. Gibbs free energy. And yeah, delta G has to be negative whenever delta S universe is positive, and positive whenever delta S universe is negative. So for a spontaneous process, delta G less than 0 means spontaneous, and delta G greater than 0 means non-spontaneous. And delta G equal to 0 means, well, neither spontaneous nor non-spontaneous. There's just no process that occurs. And as you can see, spontaneity depends on temperature. Spontaneity depends on the temperature. So you can't just look up the delta G of reaction from a data table. Yes, there were delta G values shown in the data table that I had up earlier. There are delta G values listed here. Right? This whole column is a bunch of delta G values. But these delta G values are for a specific temperature. They are for 25 degrees Celsius, 298 kelvins. In fact, you can verify this. Pick any one of these. Let's do copper oxide solid, and let's calculate it and show that that is the case. So let's see, negative 157.3 is the delta H. I guess I'll do it up here. Oh, wait, you can't see. Let me pull that down. Okay, there we go. So delta H equals negative, what did it say, 157.3. Negative 157.3 kilojoules per mole. Be careful with the units because the entropy is given in joules per mole Kelvin. Delta S is 42.63 joules per mole Kelvin. And they told us delta G is negative 129.7 for copper 2 oxide. That's in kilojoules per mole. Okay, let's see whether or not they did this at 25 degrees Celsius. I strongly suspect it is. They didn't say that it was at 25 degrees, but usually the way they set up these tables, if there are delta G values given, they're specifically for 25 degrees Celsius. So let's see, delta G equals delta H, which is negative 157.3, minus T delta S. If the temperature is 25 Celsius, that's 298 Kelvin, times delta S. I need to convert this to kilojoules, so it'll be 42.63 times 10 to the negative 3 to convert it from joules to kilojoules. And let's see what that is. Negative 157.3 minus 298 times 42.63 times 10 to the negative 3 is negative 170. Okay, that doesn't seem right. Was it at 273 by any chance? No, that's not right either. What did they do? Where are they getting negative 129.7 from? Did I do my math wrong? It doesn't look like it. That is so odd. Well, at the very least, we've discovered that the delta G at room temperature for copper 2 sulfide, or no, not copper 2 sulfide, copper 2 oxide, is negative 170.0 kilojoules per mole, which disagrees with the value on the table, which just goes to show you that you probably shouldn't be relying on data tables to calculate the delta G of a reaction. I mean, if you know what temperature the delta G values are given for, and you happen to be calculating delta G for a reaction that is at that temperature, then yeah, go right ahead and use the delta G values from the table, do delta G products minus delta G reactants, the same way you would do for delta H or delta S, but the safer bet is to just use this formula to calculate your delta G's every time. It's a pretty simple formula, so I don't see any reason why you should be avoiding it. I'll have to dig into that later and figure out at what temperature did they list these values for, because they don't even mention it in the title for the appendix even. It just says select thermodynamic properties for standard thermodynamic properties for selected substances. It doesn't say selected substances at whatever temperature they measured these at. That is so weird. Okay, so that's delta G. And of course, there's a delta G standard, which is delta G measured at standard conditions. Standard conditions being all pressures, 1 atmosphere, all concentrations, 1 molar. Now, delta G is connected to the equilibrium constant. If I were to write some chemical equation that achieves an equilibrium, like the formation of ammonia, I know earlier we wrote it with single arrows, but whoops, no. N2 plus 3H2 yields 2NH3. So if I wanted to calculate delta G at some point in this process, then I would say that delta G equals some sort of standard delta G value plus RT natural log of Q, where R is the ideal gas constant in joules or kilojoules per mole Kelvin, typically kilojoules, so 8.314 times 10 to the negative 3. Temperatures in kelvins, and the natural log of Q. Q is the reaction quotient. It's the product to reactant concentration or pressure ratios at a given point in the reaction, not necessarily at equilibrium. So this actually bears a resemblance to the Henderson-Hasselbalch equation, the same way that pH equals pKa plus log base over acid. Instead of log base over acid, you've got the natural log of products over reactants. That's what the reaction quotient is. And yeah, the same way that pH is like some starting value, some benchmark value modified by some log, your delta G is also some sort of standard or benchmark delta G value modified by, well, the product of some log. So there is a little bit of resemblance, there is a little bit of similarity in the pattern for these two equations, and in the next chapter we will see yet another equation that bears a resemblance to both of these. It has a similar format to it. So let's figure out first how you would determine delta G standard. If the reaction is at equilibrium, then neither the forward process nor the reverse process is spontaneous. So in that case, delta G would be 0. If your Q was less than K, then the forward process would be spontaneous and your delta G would be negative. If Q was greater than K, then your reverse process would be spontaneous and your delta G would be positive. If you are at equilibrium, then Q is equal to K and delta G overall is 0. So at equilibrium, delta G is 0 equals delta G standard, which is going to be unique for each individual reaction, the same way that pKa is unique for each individual weak acid. 0 equals delta G standard plus RT ln of, at equilibrium, Q equals K. Subtract RT ln K on both sides of the equation, and you get delta G standard for any reaction is negative RT ln of K. But which K? Is it Kp or is it Kc? Well, it turns out that it's both. Now, Kp and Kc will often be different values, so you'll get different delta G standards based on which one you use. So how do you know which one to use? If it's gases, then use Kp. If it's aqueous substances, then use Kc. So yeah, for gases, use pressures to calculate K. For everything else, use concentrations. For the longest time, I thought you would always have to convert it to Kc, but I asked around, and apparently that's not the case. Apparently the delta G values that they put in data tables are based on Kc for aqueous substances and Kp for gases, because that's not confusing at all. Anyway, delta G equals negative RT ln K. We can rearrange this. We can rearrange this and say that ln of K is equal to negative delta G standard over RT. And if I exponentiate both sides, e to the ln K equals e to the negative delta G standard over RT. E to the ln cancels out, so you're left with K, the equilibrium constant, equals e to the negative delta G standard over RT. All right, so that's how you would calculate the equilibrium constant if you know the delta G standard, and how you would calculate delta G standard if you knew the equilibrium constant. Typically delta G is going to be in kilojoules per mole, so R is going to have to be in kilojoules per mole Kelvin. I know I stated that before, but doesn't hurt to reiterate. Okay, what's so standard about delta G standard then? Well, if you are under standard conditions, then all concentrations and all pressures are 1. So what's Q going to be? Whether it's a gas or whether they're gases or aqueous substances, Q is going to be either concentrations of 1 molar raised to whatever exponents over concentrations of 1 molar, or it'll be pressures of 1 atmosphere raised to whatever exponents over pressures of 1 atmosphere. Whether you're dealing with gases or aqueous substances, under standard conditions, Q is going to equal 1. And what's the natural log of 1? It's 0. So under standard conditions, delta G equals delta G standard plus nothing. Delta G equals delta G standard when Q equals 1. Q equals 1 under standard conditions. That's why it's called delta G standard. So yeah, there you have it. Is there anything else I want to say about this before we look at more problems? I don't think so. I think that's pretty much it. So if you have a reaction and you don't like its delta G standard, maybe it's not spontaneous enough, or maybe it's too spontaneous and you want to lower or raise delta G, then fine, just play around with the ratios of the product and reactant, the same way that we tried to control the pH by playing around with the ratio of acid and base. Again, lots of similarity between this and the Henderson-Hasselbalch equation. And yeah, that's pretty much it. There isn't much more to go over. I don't know if I said it before, but in terms of skills that you need to learn, it's a pretty easy chapter. In terms of concepts you need to wrap your head around, it may take some time. So yeah, let's just comb through these problems, see if we have anything interesting, and it looks like we'll be finishing up a little early this time. But I'm sure we'll make up for it later. Is the next chapter going to be that quick? Well, the next chapter has a few more detailed topics, so maybe not. Maybe it won't go by as quickly, but it'll probably also be quicker than our average video length. But I'm not making any promises. Anyway, let's have a look at some of these problems. Get used to working with delta G and its relationship with K. And, oh, actually, there is one thing I almost forgot. Before we do any problems. Let's go back to this equation. Delta G equals delta H minus T delta S. So you're going to get 4 different types of reactions. Delta G equals delta H minus T delta S, or under standard conditions, delta G standard equals delta H standard minus T delta S standard. Either way you choose to write it. When delta G is negative, we say that the reaction is spontaneous. We also have a word for this, the same way that a negative delta H is exothermic, a negative delta G is called exergonic. And a positive delta G for non-spontaneous processes is called endergonic. So the same way we have exothermic and endothermic for enthalpy, we have exergonic and endergonic for free energy. And you might be wondering, well, what are the names for a positive and negative delta S? And I've looked around. Apparently there is no name for it. If I had to make up a name, I would make up the names exentropic and endentropic. But officially, there is no name for processes with a positive delta S and processes with a negative delta S. Anyway, predicting whether or not a process is going to be exergonic or endergonic based on whether it's exothermic or endothermic and whether it has a positive delta S or a negative delta S. There's 4 possibilities that you could run into, and they're all summarized in this chart. So 4 possible scenarios. Scenario 1 in the top left corner is when delta H is positive and delta S is also positive. In that case, looking at our equation, you'd have a positive minus a positive. Is that going to be positive or is that going to be negative? Well, it depends on the sizes, because if I do a large positive like 10 minus a small positive like 2, that's going to be positive. But if I do a small positive like 3 minus a large positive like 11, then that's going to be negative. So it really depends on the relative sizes. If this term is small, then delta H dominates. So when is this term small? Whenever the temperature is really low. When the temperature is really low, you're multiplying the delta S by a number that effectively shrinks it down, allowing delta H to dominate. So in this case, in the case of an endothermic process that also has a positive entropy change, low temperatures allow the endothermic term to dominate, leading to a positive delta G, and high temperatures lead the entropy term to dominate, leading you to a negative delta G. So when delta H is positive and delta S is positive, the process is spontaneous at high temperatures and non-spontaneous at low temperatures. And high and low are relative concepts, because you might have some reactions for which a high temperature is like 50 kelvins, which is not high at all. It's just that once you're above 50 kelvins, your T delta S is big enough to overcome the delta H. So high doesn't necessarily mean what you think it means. High temperature just means high enough for T delta S to be greater than delta H. And low temperature means, well, anything below that high temperature. So high and low are relative concepts here. Keep that in mind. Okay, so that's that top left corner. Bottom left corner, when delta S is negative and delta H is positive, that's going to lead to a process that's always non-spontaneous. That's going to lead to a process that's always not thermodynamically favorable. An endothermic process is not thermodynamically favorable, and a process that decreases entropy is not thermodynamically favorable. In terms of the math, endothermic means that delta H is positive. If delta S is negative, then you've got a positive minus a negative. That's always going to be positive. If I did something like 14 minus negative 8, that's 14 plus 8, that's 22. It's always going to be positive. So it's always going to be non-spontaneous if delta H is positive and delta S is negative. If we look at the top right corner, we've got the exact opposite of that. Delta H negative and delta S positive. In that case, you would have a negative minus a positive, which is always going to be a negative. If I tried something like negative 12 minus 5, that would be negative 17. A negative minus a positive is always negative, so in that case, when you have an exothermic process that increases entropy, both of those are thermodynamically favorable factors. You're always going to get a spontaneous process under those conditions. And the fourth case in the bottom right corner is when you have an exothermic reaction that decreases entropy. Exothermic reactions are thermodynamically favorable, but reactions that decrease entropy are not so favorable. So there's a competition between the enthalpy and entropy terms. And of course, at low temperatures, the enthalpy dominates. At high temperatures, the entropy term dominates. So in this case, let's see, it's a negative minus a negative. If this negative is small, negative minus a small negative is still negative. So at low temperatures, you would have a negative delta G, a spontaneous process. And at high temperatures, it's a negative minus a large negative, which is ultimately going to be positive, leading to a non-spontaneous process. So I would recommend, rather than memorize this chart, try to understand mathematically why things work out the way they do. Positive minus positive, positive minus negative, negative minus negative, negative minus positive. Think about what kinds of signs you can get from each of those four scenarios. As long as you understand it from a mathematical perspective, you won't have to memorize. Okay, now let's go ahead and do some problems. Okay, what is the difference between delta G and delta G standard for a chemical change? We already explained. 31. A reaction has delta H standard is 100 kilojoules per mole and delta S standard is 250 joules per mole Kelvin. Is the reaction spontaneous at room temperature? Let's see. Delta H and delta S are both positive, so there's a competition. At room temperature, T is 298 kelvins. Let's go ahead and figure this out. Don't forget, delta S is in joules. You need to convert it to kilojoules. Or you need to convert delta H to joules, but usually kilojoules is what you want to stick with. So we've got delta G, or delta G standard in this case, equals 100 minus T is 298 kelvins. And then delta S, I need to convert it to kilojoules. 250 joules is 0.250 kilojoules. And let's see what that's going to be. 100 minus 298 times 0.250 is positive 25.5. Since it's positive, that means it's going to be non-spontaneous at room temperature. And I guess we can ask as a bonus question, at what temperature does this process actually become spontaneous? Where's that threshold temperature between spontaneity and non-spontaneity? And that's not too hard to figure out. Set delta G standard to 0 and solve. 100 minus T times 0.250. Let's see. So add T times 0.250 over to the left, divide by 0.250, and we get T equals 400 kelvins. So at a temperature of 400 kelvins, it is neither spontaneous nor non-spontaneous. Above 400 kelvins, it's spontaneous. Below 400 kelvins, it's non-spontaneous. All right. 32. Explain what happens as a reaction starts with delta G less than 0 and reaches the point where delta G is equal to 0. So it starts with Q less than K, and the reaction proceeds until it reaches equilibrium. That's basically it. 33. Use the standard free energy of formation data in Appendix G to determine the free energy change for each of the following reactions. Okay, so here they're telling you, which are run under standard state conditions and 25 degrees Celsius. So like I was saying before, the delta G values in that table are for 25 degrees Celsius, but I don't know why the calculation I did didn't work. Maybe they just listed that value wrong and I happened to pick an item that had a typo in it. I don't know. But yeah, using data tables to calculate delta G, not too hard. Delta G products minus delta G reactants. We did it earlier with delta S, and if you need more examples, go back to video number 6 where we did a lot of that with delta H. At least I think we did a lot of it. I think we did sufficient examples, let's put it that way. All right. Off to the next page. Use the energy data again. We'll skip that. 35. Given those values, determine the standard free energy of formation for phosphoric acid. How does your calculated result compare to the value in Appendix G? Explain. Let's see. So again, this is just a matter of rearranging the equations and adding them up to get your desired equation. So it's the energy of formation for phosphoric acid that we need to write. In case you've forgotten it from video number 6, the enthalpy of formation was the enthalpy associated with forming a compound from its raw component elements in their naturally occurring form. So the standard free energy of formation for phosphoric acid is the delta G associated with that same process. So phosphoric acid, H3PO4, formed from hydrogen, phosphorus, and oxygen. So natural hydrogen is diatomic hydrogen gas. Natural oxygen gas is O2, of course, and natural phosphorus is usually in the form of P4, white phosphorus, I believe, which is in the solid state. And as for phosphoric acid, I have no idea if they wanted it in the gas state or the liquid state, or, well, not liquid state, but aqueous state. I would imagine they'd want it in the aqueous state, but I guess if you go to your data table, it'll only be available in one state and not the other. Let me look it up. Where is phosphoric acid? I guess these are listed in alphabetical order, so P's. Okay, let's see. Phosphoric acid. Okay, they have phosphoric acid in liquid form and in solid form, so I'm not sure which one they were referring to. I would assume liquid. Actually, wait. No. I know. If we look at the problem itself, yeah, they show phosphoric acid in the liquid state, so that's what they want. They want it in the liquid state, so scratch that. Liquid. Okay, and yeah, rearrange the 3 equations that they gave you until you get this. It's just applying Hess's law. If you multiply an equation, you multiply the delta G associated with that equation. If you flip an equation, then you take the negative of the delta G associated with that equation, and if you add 2 or more equations, then you add their delta G's. Same thing we did earlier with delta S, same thing we did way back in video number 6 with delta H. So yeah, I think that's enough for you guys to go on. I think you can figure out the rest from there. Let's take a look at this next set. Is the formation of ozone from oxygen spontaneous at room temperature under standard conditions? You'd have to look at the data tables and calculate the delta G to answer that. 37. Consider the decomposition of mercury 2 oxide. Is the decomposition spontaneous under standard conditions, and above what temperature does the reaction become spontaneous? All right, we already did something like that earlier where we calculated a temperature of 400 kelvins, at which point, well, above which a reaction is spontaneous, below which it's not. So we already showed how to do something like that. 38, among other things, an ideal fuel for the control thrusters of a space vehicle should decompose in a spontaneous exothermic reaction when exposed to the appropriate catalyst. Evaluate the following substances under standard state conditions as suitable candidates for fuels. Okay, so you would calculate all their delta G values, and whichever one has the most negative delta G would be the best fuel. A negative delta G is spontaneous, but the more negative it is, the more spontaneous it is. The better it is as a form of fuel because it will burn spontaneously. You don't have to put in energy to make the process continue. I mean, you do have to activate the chemicals. You do have to put in the activation energy, but after that point, the reaction carries on its own. Okay, 39. Calculate delta G standard for each of the following reactions from the equilibrium constant at the temperature given. Okay, this we haven't done yet. Let's take a couple of these. So it doesn't matter if it's a Kp or a Kc. They will give you the appropriate K for the delta G that they want, or the appropriate delta G for the type of K that they want. And you'll know which type of K is the appropriate one because if it's gases, it's Kp, otherwise it's Kc. So you don't need to do any Kp, Kc conversions, at least not unless they give you a reaction involving gases and they give you Kc, or they give you a reaction not involving gases and they give you Kp, which I don't even know how you would define a Kp for non-gases, but I digress. So let's do a couple of these. Let's do A and... Yeah, let's just do A, B, and C. So... First one, Kp is 4.1 times 10 to the negative 4, and the temperature is 2,000 degrees Celsius. That's going to be delta G standard equals negative RT ln of K equals negative 8.314 times 10 to the negative 3 kilojoules per mole Kelvin times the temperature in kelvins. They said 2,000 degrees Celsius, that's 2273 in kelvins, times the natural log of K, which was 4.1 times 10 to the negative 4. All right. That gives us negative 8.314 times 10 to the negative 3 times 2273 is negative 18.90 times ln of 4.1 times 10 to the negative 4. So that's natural log of 4.1 times 10 to the negative 4 is... Let's see, that's going to be, so 2 sig figs, 2 decimal places, that's negative 7.80. And multiply those and that'll give us 3 sig figs. So 18.90 times 7.80 is 147. 147 kilojoules per mole. next one, pretty much the same thing. T is 400, Kp is 50. So delta G standard equals negative 8.314 times 10 to the negative 3 times, they said the temperature was 400 Celsius, so that's 673 in kelvins, times natural log of 50.0. What will that be? So negative 8.314 times 10 to the negative 3 times 673 is negative 5.60. Negative 5.60. And then natural log of 50.0, that's 3 sig figs. So 3 decimal places, that's 3.912. So negative 5.60 times 3.912 rounded to 3 sig figs is negative 21.9. Negative 21.9 kilojoules per mole. And I see this marker is also fading. That's what happens when you try to use your markers equally. They all die together. And then part C, we've got 980 Celsius and 1.67 for our K value. So delta G standard is negative 8.314 times 10 to the negative 3 times, they said 980 Celsius, 980 plus 273 is 1253 times natural log of, was it 1.67? Yeah. Okay. Negative 8.314 times 10 to the negative 3 times 1253 is going to be negative 10.42. And then ln of 1.67, 3 sig figs, 3 decimal places, so that's 0.513, 0.513 times negative 10.42, 3 sig figs, that's negative 5.35. Negative 5.35 kilojoules per mole. Okay, and I think now all we need is a couple examples of doing the opposite, and then that'll be pretty much everything we need to cover for this chapter. There really isn't much to it. I mean, the amount of time I spent in the beginning on entropy was already more time than your teacher will probably spend if you're actually taking a chemistry class. If you're just doing independent learning, then you're already getting more than what students typically get in school. So yeah, we're done with that page, but if you want to solve parts D, E, and F on your own, I would strongly recommend that. 40, calculate delta G standard for each of the following, so more of the same. 41, calculate the equilibrium constant. Here we go. So the reverse process, they give you delta G standard, and they want you to calculate the equilibrium constant. Let's see. So I'm given, I guess let's get a new sheet out, and let's actually switch to our camera. So I guess I didn't tell you which ones I would pick. Let's do just A and B. And actually, you can make predictions just based off of the sign of delta G standard what K is going to be, if it's going to be a large K or a small K, if it's going to favor products or favor reactants at equilibrium. But yeah, let's do parts A and B. So part A, delta G standard is negative 9.2. K is going to be e to the negative delta G standard over RT. RT is always going to be a positive value, so negative delta G standard. If it's spontaneous, then negative delta G standard is positive because delta G standard is negative. And if it's non-spontaneous, then it's negative times a positive, so you'd get a negative. If you get a negative exponent, then you're going to get a really small k value, such as your Ka values and your Ksp values. If delta G is negative, on the other hand, then a negative times a negative, being a positive, would give you probably a large k value, like the formation constants for complex ions, which we didn't really talk about, but those k's are usually pretty big. So yeah, the more spontaneous the forward reaction is, the larger the K value, the more heavily the equilibrium lies towards products. And that should make sense to you intuitively. That should make sense. If a reaction likes to go forward a lot, then it's very spontaneous. Okay, so our delta G standard was negative 9.2 kilojoules per mole. They just said kilojoules, but same thing. So K equals e to the negative 9.2. That's in kilojoules, so R needs to be in kilojoules per mole Kelvin. 8.314 times 10 to the negative 3 times the temperature. They said the temperature was room temperature, so 298 kelvins. All right. So 8.314 times 10 to the negative 3 times 298 is going to round to 2.48. Is going to round to 2.48. So that's e to the 9.2 over 2.48. And then 9.2 over 2.48 is 3.7. E to the 3.7. 1 decimal place means 1 sig fig. So e to the 3.7 is going to be 40, or 4 times 10 to the 1. 40, or 4 times 10 to the 1, to show that it's got only 1 sig fig. Okay, part B. Same temperature. Delta G is 7.3 kilojoules. So if it's the same temperature, then it's the same RT value of 2.48. So we don't have to bother recalculating that. K equals e to the negative. They said 7.3 kilojoules over 2.48. So that's going to be 7.3 over 2.48 equals 2.9. So That's e to the negative 2.9, which equals 0.06. 0.06. One decimal place in the exponent gives you 1 sig fig. So, yeah, 0.06 or 6 times 10 to the negative 2 is how we would usually write an equilibrium constant. So there you go. That's a reaction that favors reactants over products. And you can do the rest of these on your own. Okay, I think I've covered at least one example of everything that was absolutely necessary to cover, so for the rest of these problems, unless I see something that stands out, I'm just going to put them on the screen for you for a few seconds so that you can grab them for additional independent practice. 42. Already did something like it. 43, basically the same as the previous two problems, except they don't give you delta G. You have to calculate it from data tables. .44, same as 43. Nothing too interesting about 45. Determine the normal boiling point of dichloroethane. Find the actual boiling point using the internet or some other source and calculate the percent error in the temperature. Explain the difference. Okay, this is a little interesting. So, to get the boiling point of something in the context of thermodynamics, by taking advantage of delta G, basically the boiling point is the point above which vaporization is a spontaneous process. Oh, so we have a process that's spontaneous above a certain temperature and non-spontaneous below that temperature. That should remind you of this chart. Something that's spontaneous at high temperatures and non-spontaneous at low temperatures. That's the top left corner. So basically, you're going to take the delta H minus T delta S and set it equal to 0 to solve for the T where, delta G is 0, and then that T is the boiling point. So you would find delta H and delta S for dichloroethane liquid turning into dichloroethane gas. And then just take delta H minus T delta S, set it equal to 0, solve for T. That's your boiling point. So that's how to handle something like 46 using thermodynamics concepts. (47) Under what conditions is N2O3 decomposition spontaneous? Find the delta H and delta S and then figure out which of the 4 cases you're dealing with in terms of delta G. It could always be spontaneous. It might never be spontaneous. It might be spontaneous at high temperatures, or it might be spontaneous at low temperatures. Figure out which one of the four cases it is, and that's all it's asking. 48. Using this information, calculate the standard free energy change for the aqueous reaction of hydrogen ion with hydroxide ion to produce water. Hint, the reaction is the reverse of the self-ionization reaction. Yeah, you can do that. If you flip a reaction, you take the reciprocal of its equilibrium constant, and if you've got the equilibrium constant, and I think they said it was room temperature. Yeah, it's at room temperature. So you've got the constant, you've got the temperature, you know the ideal gas constant, so you can calculate delta G standard. 49. What is the equilibrium constant? Just use delta G. And the temperature, of course. 50. What is the equilibrium partial pressure? Okay, so now they're kind of getting into the integrated problems where they want you to make use of concepts from other chapters. So use what you've learned about thermodynamics in this video to get the equilibrium constant, then use that K value to calculate the pressure. Set up your ice table if you need to. I don't think you're going to need one for this case because there's only one gas and everything else in the reaction is solid. But, you know, that's what you would need to do. 51. Looks like it's talking about finding partial pressures, so I think we'll pass on that. Okay, pass on 52, pass on 53. Would the reaction vessel need to be heated or cooled to keep the temperature of the reaction constant? To keep the temperature of the reaction constant. I guess if it's endothermic, then it would need to be heated, and if it's exothermic, it would need to be cooled? Yeah, I'm not sure what they're getting at with that question. 55. Let's see, we've got a dimer, which is a polymer with two components. You don't really need to know about polymers, unless maybe you're doing IB chemistry. Oh, okay, this time they ask you for delta S for problem 55. Easy enough. If you know the delta H, which is given in terms of the hydrogen bond strength, the 66.5 kilojoules per mole, and you know the temperature and you know the equilibrium constant, you can use that to get delta G, and then use the delta G equals delta H minus T delta S to solve for delta S. Same old equation, just a slightly different use for it. 56, determine delta G for the following. We've already done stuff like that. They're just adding more steps to it, involving concepts from past chapters. Okay, moving on. 57. Oh, I don't think I remembered to mention this. Delta G of formation, just like delta H of formation, is defined as 0 for raw elements in their naturally occurring states. I don't know if I mentioned that before, but if I didn't, there you go. You'll even see that when you look at data tables. You'll see delta H and delta G of formation. Whenever one is 0, the other is also 0. But yeah, what did 57 say? Determine the solubility product using delta G. We've shown how to calculate Ks from delta Gs. 58. Is the reverse of 57. 59. Diamond to graphite. So I guess they want you to use data tables to figure that out. Number 60, evaporation of water. Okay, yeah, you know how to do that. You guys can figure out how to do that on your own. Might take a little bit of thinking for the later parts, but you know how to do them. We've covered everything you need to know. 61 looks like more of a biology question than a chemistry question. '62, is that also a biology question? Kind of. Oh, hold on. So it says calculate delta G when the concentrations of G6P and F6P are 120 micromolars and 28 micromolars respectively. Okay, so for this one, it looks like they're going to have you use the full delta G equals delta G standard plus RT ln of Q. So you would have to calculate Q, the product to reactant ratio, and use the appropriate exponents. It looks like everything is 1 to 1 in those equations that they give you for 61 and 62. I don't know if 61 is related, but yeah, that's not anything new. I mean, we haven't used the full delta G equals delta G standard plus RT ln Q, but you're rarely asked to do that anyway. And it's not as if it's that hard to plug numbers into it. 63. Without doing a numerical calculation, determine which of the following will reduce the free energy change for the reaction, that is, make it less positive or more negative when the temperature is increased. Explain. When the temperature is increased. Let's see. So you would have to know... Okay, I think I see what they're getting at. So, again, they're using the full delta G equilibrium formula. They're using delta G equals delta G standard plus RT ln of Q. And they're asking about the effect of increasing the temperature. So if ln of Q is a negative, then increasing the temperature will make delta G more negative. If ln of Q is positive, then increasing the temperature will make delta G more positive or less negative. So yeah, that's what they're getting at there. At least I think that's what they're getting at. Or do they mean when it's at equilibrium? Or maybe they're just talking about the standard free energy change. If it's at equilibrium, then maybe they're just talking about delta G standard equals negative RT ln of K. In which case, if ln of K is positive, and you multiply by that negative sign, increasing the temperature will make delta G more negative. If ln of K is negative, multiplied by that negative as a positive, increasing the temperature would then make delta G more positive or less negative. Okay, so yeah, depending on which interpretation you take, and I'm leaning more towards this one now. I think they meant for you to use this. But yeah, depending on which one, you get the basic idea of what they're trying to ask there. Okay, it's not that hard. And one last sheet before we wrap things up. Let's see, when ammonium chloride is added to water and stirred, it dissolves spontaneously and the resulting solution feels cold. Without doing any calculations, deduce the signs of delta G, delta H, and delta S for this process and justify your choices. Okay, you already know what to do here. What does it mean for the water to get cold? Is the dissolution process exothermic or endothermic? They already told you that it dissolves spontaneously, so is delta G positive or negative? And then if you take a solid solute and you turn it into, or if you take a solid and you dissolve it, you change it to the aqueous phase, what happens to delta S? Is that going to be an increase in entropy or a decrease in entropy? You know everything you need to know in order to answer this question. 65. Determine delta G standard, so I guess they want you to use data tables there. The reaction with oxygen yields sulfur dioxide as the only product. Write an equation that describes this, and okay, so that's just a separate reaction. And then C. By combining the equations from parts A and B, write the equation that describes the roasting of the chalcocite, and explain why coupling these reactions together makes a more efficient process for the production of the copper. If you combine them and you combine their delta G values, then I would imagine it's going to end up with a delta G that's more negative, which means it's more spontaneous, which means it just happens more readily. The equilibrium lies further to the right. The yield of product is higher. At least that's my prediction without doing any calculations. And then 66. What happens to delta G for the following chemical reactions when the partial pressure of oxygen is increased? Okay, Le Chatelier. So, if the partial pressure of oxygen is increased for reaction A, then that shifts equilibrium to the right. If the forward reaction is getting a boost, if you're shifting right, then that increases spontaneity. Part B, same thing, increasing oxygen would shift you right, so that would increase spontaneity, that would make delta G more negative. Part C, it's a product, so if you add oxygen, that shifts equilibrium left, which makes the delta G more positive, or less negative if it happens to be negative. Okay, yeah, that's pretty much it. So that's thermodynamics. In the next video, we will cover electrochemistry, which does involve thermodynamics concepts and therefore also involves some equilibrium concepts as well. So make sure that you're on top of things from this chapter before taking a look at electrochemistry. Not that you can take a look right now because I haven't recorded that video yet, but you know, once it's out. So, yeah, electrochemistry is coming up next. You might want to review video number 4 where I covered redox reactions because that's also coming back up. So if you've forgotten oxidation and reduction, the time to review is before the next video. And that's it for me. This has been Al the Tutor reminding you once again that ignorance is not bliss. Take care, and I will see you in the next video.